Hello, welcome one and all to the 14th episode of Dyllon Explains Everything. And before we get into the episode, I wanted to point out that this episode was actually filmed when I made my combinatorics episode. But it was unused footage that made the video too long, so I took it out. But this upcoming week, or when this comes out, it will be the week that's ending, I'm going to be away at a camp, so I'm not going to be able to make a video. But be assured that the 15th episode will be a normal episode. With all that being said, I hope you enjoy the video, and thank you all for subscribing, liking, and sharing this with your friends. It means a lot to me. Now, this isn't really interesting on its own, it's just combinations, it's not really that important, but what is important is triangle numbers and other geometric numbers, which really aren't important at all. But you may have heard of a square number, where you take a number and take it to the power of 2. But what would it be if we had a triangle number? Well, let's say we had a 0th dimensional number. This would literally just be a point of nothingness. It would have no width, no height, and no length. So every 0th dimensional number is 0. The first 0th dimensional number is 0. Second one is 0. Third one, 0. Fourth one, 0. In the first dimension, every number is literally just itself. The first dimensional number is 1, the second one is 2, and the third one is 3, and so on and so forth. This is because all it is a line, and all we're giving it is the length of the line. Once we get into the second dimension, we need to define what shape we're using as well, because not only is there length, there's also width, and the way we show this width can be done in different ways. For example, if we had a square, we're showing that the length and the width are equal. So the first second dimensional square number would be 1, because 1 squared is 1. The second dimensional square number would be 4, because 2 squared is 4. 3 squared is 9, 4 squared is 16, so on and so forth. So how can we visualize square numbers? Well, first of all, the first dimensional square number has a length of 1. And since it's a square, we don't actually add anything, it's just 1. That's why the first square number is 1. Now if we go to the second square number, the length has to be 2, and so does the height. And it has to be a square, so we have to put in that dot. That gives us a 2 by 2 square, which is 4. And we can go on and on forever to find all the dimensional square numbers. So how can we visualize triangle numbers? Well, triangle numbers are really just half of squares. So if we have a triangle that's 4 high and 4 long, then we know that we need to have all the points in between. So really, that's just a triangle number right there. So this is 4 plus 3 plus 2 plus 1, which is 10. If you want another visualization for triangle numbers, you can really think of it as just adding the next number every time. You start out with 1, and then you add 2 for the second triangle number. Then you take that and add 3 for the third triangle number, and so on and so forth. Knowing that, we can start filling these in. So now that we can visualize triangle numbers, and now we can fill them in this little chart here, can we actually find a pattern or a formula for these triangle numbers? The formula for triangle numbers is this right here. Now, if you look at this, what this is really doing is taking the average of all numbers 1 to n, and then multiplying it by n. So now that we know what triangle numbers are and square numbers and how to visualize them, what if we go to the third dimension with cube numbers and tetrahedron numbers? Well, we know cube numbers are just whatever number is cubed. So for example, 1 cubed is 1, 2 cubed is 8, so on and so forth. What would a triangular number be in the third dimension? The formula for these 3D triangular numbers looks something like this, which looks relatively similar to that. You can see we're just multiplying by n plus 2, and then we're also multiplying this by 3. Now, what this is really saying is that we've got the first triangular number, then we've got the second triangular number under that. So we add the first 2 triangular numbers, which you can see here. This is really just adding the first 2 triangular numbers. 1 plus 3 is 4. This is adding the first 3, 6 plus 4 is 10, and this is adding the first 4, because 10 plus 10 is 20. Now if you want the proof for this formula, you can go look that up on your own. It's extremely difficult to explain to people who may not know the advanced mathematical concepts that I don't even understand. Now if you want to find the formula for triangular formulas, we can look at the first dimensional triangular number, which is just whatever layer we're in over 1, so it's just that number. If we look at the second dimensional triangular number, which is just a normal triangular number, we can see that's the equation I showed earlier. Now if we look at the third dimensional triangular number, we can see that that's the other formula I showed earlier, but we can find a pattern. If we look at the difference between this one and this one, we can see that we're just multiplying by n plus 1 over 2. If we look at the difference between this one and this one, we're multiplying by n plus 2 over 3. This follows the same pattern throughout every dimension. The formula for finding these formulas is this, where we have the nth layer of the nth dimension, which you can see over here. For example, if we're trying to find the third second dimensional triangle number, this is the second dimensional triangle numbers, and this is the third one. Now, we can put 2 in for m, because that's the dimension, and 3 in for n, because that's the layer. So, if we plug in 3 for the layer and 2 for the dimension, we get this. Now, if we work this out, 3 plus 2 is 5, 5 minus 1 is 4. 4 factorial is 4 times 3, which is 12, times 2, which is 24. Then, if we work out the bottom, 2 factorial is just 2. 3 minus 1 is 2, so 2 factorial times 2 factorial, which is just 2 times 2, which is 4. And then when you divide these, we get 6, which, if we look here, that's what we were trying to get. This formula right here is the formula I was just talking about. This is for finding the nth m-dimensional number, where m is the dimension and n is the layer. Now, we can simplify this into a binomial coefficient. In order to prove that these two things are equal, I'm going to work this out here. So, if we are putting this in place for n, what we get is we're just putting this on the top and we're turning it into a factorial, which is exactly what we have here. Now, when we go to this part, we're just putting m in for r, which is exactly what we have. This is where it gets a little tricky. N minus r. What we're really just doing is taking this top part and subtracting the bottom part. If we have n plus m minus 1, and we subtract m, then these two m's just cancel out. And we're left with n minus 1, which is exactly what we have right there. This isn't the only formula out there for geometric numbers. If we were trying to find the nth m-dimensional square number, that's just n to the m, because we've got the nth number and the mth layer. So if we were trying to find square numbers, this would just be 2, and we'd have whatever number we have to the second power, which is what I proved earlier with this. Now, there's other formulas for other types of geometric numbers, for example, hexagonal numbers, and then three-dimensional hexagonal numbers, and then there's formula for finding those formulas that no one cares about. Now, whether you think these are useless, fun to learn, or you skipped to the end because you were tired of me talking, you are all almost correct. With that being said, if you enjoyed the video you saw today, why not click subscribe to see more and click the like button to let me know you did like it. And if you have a suggestion for a Dylan Explains Everything, leave it in the comments below. And until we meet again, my name's Dylan and I explain everything.